On behalf of the RSI, along with my colleagues from the Keck Institute for Space Studies and the Linde Center for Global Environmental Science, Tom Prince and Paul Wennberg respectively, I'd like to welcome you to today's panel discussion titled Human Impacts on the Atmosphere as Revealed by COVID-19. As we're all familiar, 2020 continues to present society with remarkable challenges. While efforts must continue to minimize the health and economic damage caused by COVID-19, and as we're painfully reminded, we must collectively act to stamp out racism in its various insidious forms, the climate crisis continues unabated and without, I might add, the hope of a vaccine. Our work in climate research and ever more sustainable technologies is as important as ever. One silver lining of this unusual period in time is that we're able to bring online content like today's webinar to a broader audience than we're otherwise able to conveniently reach. We plan to continue to bring you accessible science-based content on important issues around climate change and the stewardship of our natural resources. Turning to the topic of today, the changes in the economy due to the COVID-19 response, in principle, offer an opportunity to see with greater clarity the effects of human activity and human-induced emissions on the atmosphere and the climate systems. We've assembled a group of experts today to talk about what we've learned and what we might learn going forward. So with that, it's my sincere pleasure to introduce the moderator for today's panel, Dr. Jessica New, who's a research scientist at the Jet Propulsion Laboratory, aka JPL. I'd also like to introduce Anne-Marie Eldering, Deputy Project Scientist for the Orbiting Carbon Observatory 2, aka OCO2. Anne-Marie is also Project Scientist for OCO3, hailing from JPL. And then we have Christian Frankenberg, Professor of Environmental Science and Engineering, as well as Jet Propulsion Laboratory Research Scientist, and Paul Wennberg, Professor of Atmospheric Chemistry and Environmental Science and Engineering, as well as Executive Officer for Environmental Science and Engineering, and the Director of the Ronald and Maxine Linde Center for Global Environmental Science. So with that, I'd just like to make a comment about JPL and Caltech for those of you that may not be familiar. JPL is a federally funded research and development center managed for NASA by Caltech. From the long history of leaders drawn from the university's faculty to joint programs and appointments, JPL's intellectual environment and identity are profoundly shaped by its role as part of Caltech, just as Caltech's environment and identity are reciprocally shaped by JPL. We're excited to see this interconnectedness enhanced and deepened via our common cause in climate, atmospheric, and environmental research. And with that, I'd like to hand the floor over, or the webinar over to Jessica. Thanks, Jessica.
Thank you, Jonas. So hello, everyone, and thank you all for joining us this evening. Before we get to the presentations by our panelists, I want to spend a few minutes to kind of help orient you a bit with respect to how their materials fit together. So the talks that you're about to hear cover a wide range of spatial scales from sort of local to global, and a wide range of temporal scales from hours to centuries, over which humans exert our influence on the atmosphere. And each panelist is going to focus on what COVID-19 has revealed about our influence in one of three distinct regimes. So Anne-Marie will start off, and she's going to be talking about carbon dioxide, which of course affects the entire global Earth system and affects it over the course of centuries. And then Christian is going to go next, and he will talk about methane, which falls into a little bit of an intermediate regime. So it's important as both a climate gas on decadal timescales and is also a contributor to poor air quality at somewhat smaller spatial and temporal scales, although much larger still than what we sort of think of as air pollution. So Paul then will be talking about air quality gases and particulate matter, what we think of as pollution, and focusing on sort of more immediate and localized effects on the atmosphere. And so now to start us off, I'd like to invite Anne-Marie to join me to discuss the influence of COVID-19 mitigation policies on CO2 in the atmosphere. Welcome, Anne-Marie, and I'll give you the floor.
Thank you, Jessica, and thanks everyone for joining us for our discussion tonight. So if we go to the next slide, I'm sure you all can feel the impacts of our safer at home and COVID changes, and we've all had changes in our behavior. I know for myself, I'm not flying anywhere and I'm driving a whole lot less. So we might ask the question, well, what's this mean for our carbon dioxide emissions? And a group wrote a paper recently, Corinne LeClaire and her group, where they made some estimates of activity changes and then translated that into estimates of carbon dioxide changes. So you see here a time series from January through May of this year, looking at how different sectors like surface transport, industry, and power aviation might have changed. And we see at the peak, their estimate is in April, there's somewhere about 18% less carbon dioxide on a daily basis. Most of that from surface transport and power and industry. And that kind of relates to my own experience, as I said, driving, flying less, but I'm still using power at home and I'm buying things that have to be made somewhere. So it's kind of a mixed bag. So if we try to go now just from what's happened over the last few months to the larger context over the many years, the next slide, you'll see a figure that shows time series of our global CO2 fossil emissions, so emissions that come from burning fossil fuels like coal, oil, gas, etc. And this time series shows that in the 20 years from 2000 to 2020, there's been increase in emissions from 7 gigatons of carbon per year to upwards of 10. That's shown in the black line. And then the red line is kind of showing over shorter timescales what's happened in 2020. And you can see an expansion of that figure on the right. Their estimate of how much carbon dioxide emissions we'll have across 2020, where we see these decreases we're experiencing right now, but then the anticipation that we'll be back to business as usual in the later part of 2020. When you integrate those numbers, you'll see that over the whole year, somewhere between 4 and 7% less carbon dioxide produced this year by fossil emissions. And another way you might think about that is what's this year's emissions going to be like? Well, it's maybe 2011. We're not getting back all the way to 2000. We're just maybe going to be at 2011 levels. So we'll see some decrease and it'll be something like a decade ago. So then if we go to the next slide and we think about this now in the context of the world around us and in the environment we're living in, our atmosphere actually holds on to that carbon dioxide. As Jessica mentioned, it's a long-lived gas. It doesn't react away with chemistry. It very slowly goes into the ocean or the forest. It's not a quick removal mechanism. So those emissions we've been putting up there for decades and decades are accumulating, and there's now something like 885 gigatons of carbon in our atmosphere. And remember that annual emission rate was somewhere order 10. So if you think about this in pools, it's like having an Olympic swimming pool, and every day we're putting about 20 gallons of water into that. So you can imagine if somebody didn't put that water in one day, it's pretty hard to see. It's not a very dramatic change. You probably need accumulation over time before you're going to notice if there's some change in that addition each day. So the greenhouse gases like carbon dioxide, there's a lot existing in the atmosphere because they're long-lived. So an interruption in our emissions is not immediately obvious. If we go to the next page, I'm just going to give you a glimpse from the world the way I look at it. So as you heard, we work on satellite measurements of carbon dioxide from space. So the right-hand column just gives you a cartoon idea of what we're doing. We look at sun that's reflected down to Earth's surface and then back up to our satellite, and we can see how many carbon dioxide molecules there are. So we started looking at our data. We're like, oh, maybe we can see what happened with the COVID changes. And these maps I've purposefully not labeled all that well are 2 different days when our satellite instrument measured carbon dioxide over Rome. And these are both plotted on the same scale of 412 to 418 parts per million. And you can see, wow, one of these is dramatically different than the other. But actually the explanation for this difference turns out to be the weather. It's not because of changes of emissions due to COVID, but carbon dioxide is influenced by weather. It's influenced by plants, can remove it when they're very active in the spring. and it's influenced by emissions. So we have to untangle all of these things if we want to see the emissions-driven changes. Certainly the measurements from space aren't dramatically obvious where these CO2 changes are. Folks who work with ground-based measurements that are right there in the city actually do seem to see more obvious signals of changes from the CO2 emissions. So then just my last slide here, thinking about what are the implications. So this COVID change of behavior, a sudden upset to our industry and our activities has indeed changed our CO2 emissions, but it's not the path we want to get on if we want to really make a change to CO2 in a way that's going to address the growing climate problem. This is just a figure showing you from 1970 to 2017 how different sectors contribute to the fossil CO2 emissions. So this makes, an implication here is if you want to get carbon dioxide emissions reduced, we need to transform industry, we need to transform transport, we need vehicles and surface transport that are using electricity and cannot, built not around gasoline. Heat and electricity, we're already starting to see transformation to renewables like wind power, solar power, et cetera. That has to happen more dramatically to bring down these emission sources. So the challenge ahead is how do we create a sustainable future and decarbonize our industry and our transport so that our CO2 emissions can be reduced in a sustainable and manageable way. Well, thank you for letting me share my thoughts on that. We're now going to turn to Christian's presentation and he'll tell you a little more about methane. Thank you.
Hello everyone, I'll be talking about atmospheric methane in my second talk, where we will basically be going down the step a little bit towards shorter-lived greenhouse gases before Paul will really go to the very short-lived atmospheric gases that are more related to air quality compared to CO2 and methane. Next slide, please. First of all, I want to give a little bit of an introduction in the global methane budget. Primary reason for that is, unlike CO2, the methane budget might be a little bit less obvious to everyone, because for CO2, we definitely know where the major sources are coming from, at least from the anthropogenic side, where CO2 release is just basically a consequence of fossil fuel burning, mostly in terms of the sources. The methane budget is a little bit more intricate. So what we see on this slide, let me focus first on the natural sources. So the dominant natural sources of atmospheric methane is wetlands and fires, basically. This is just microbial emissions of methane under anaerobic conditions. So it's a purely microbe-driven part. And on the anthropogenic side, we have the dominant sources that are basically fossil fuel production and use. And the other big part that some people sometimes are not really fully aware of is really agriculture and waste. And maybe to give you a little bit of background, what does agriculture and waste have to do with methane emissions? It's really just creating an artificial habitat for microbes under anaerobic conditions that then produce methane. So it's kind of an indirect biological way of releasing methane, but mankind is basically providing a habitat that would otherwise not be there. The other important difference with respect to CO2 is that we have a sink for methane within the atmosphere. So the dominant sink, unlike for CO2, where both the sources and the sinks are located at the kind of interface between the land surface and the atmosphere, for methane, it's actually within the atmosphere. So it's being oxidized away within the atmosphere. That kind of makes it stand out a little bit in that respect. And the lifetime within the atmosphere is about 9 years. So whatever we are emitting today, we will see it sticking around for a decade or more. And it will be well mixed within the global atmosphere, but it's far less of a lifetime than for atmospheric CO2. Okay, next slide, please. So as a consequence of these anthropogenic emissions from pre-industrial times, the methane concentrations in the atmosphere have almost tripled currently, and this is just a time series from the South Pole. So this is from Antarctica, just chose this one because it's the cleanest time series we can have, undisturbed from any local sources of methane. So we see a steady increase in kind of the 80s and 90s. In the year 2000 to 2007, something really unexpected happened that we are still thinking about in the methane community. We basically had the methane concentrations in the atmosphere leveling off at around 1,720 ppb. And everyone was happy and thought, okay, the methane problem as a greenhouse gas is solved. But then in the year 2006, 2007, we started seeing it to increase again, and this is still ongoing. Actually got a little steeper in like 2015, 2016, and methane is still on the rise, even though we were expecting it to level off and get into this kind of steady state behavior. So that's one reason why we still are very interested as a community in atmospheric methane, because this interplay between sources and sink for methane is far less well understood than it is for atmospheric CO2. Next slide, please. So together with JPL and Caltech, in the recent years, we developed methods how we can dig a little bit deeper into anthropogenic methane emissions. And this is an example using airborne imagery. It's actually an airborne imaging spectrometer that can make methane visible from the air, basically at the kind of meter resolution. And this is an example of a methane plume emanating from a gas oil pad in the Four Corners area. And each of these little pixels is only about 3 meters big. So there we can basically unequivocally say where the methane is coming from and helping quantify the rough emissions from these sources and basically pinpoint directly to where these are located so that we can potentially mitigate. And I'll explain later a little bit why this is so important for atmospheric methane, why these sources are so uncertain. But let me first go through a couple of examples of what we can see now with these techniques. This is an example from the California's methane super emitters paper. So in panel A, you basically see compressor stations as a dominant source of methane. The next example is emissions from an oil well. The next one would go into kind of a tank of liquefied natural gas. The next one might be a little bit more unexpected. This is really a dairy manure management site. The next one would be a wastewater treatment plant. And the last but not least one would be a landfill, where typically for landfills, we would have assumed we don't really have point sources within a landfill, but methane seeping out everywhere. But it turns out that due to management practices, even for landfills, methane is predominantly coming out at very few locations. And that enables us to basically see and map these emissions directly using these techniques that we developed. Let me just say one word why we know so little about methane emissions. If you imagine we're using your gas stove to heat up water, in terms of CO2 emissions, we basically know what you will emit roughly because almost all the natural gas that you use for heating will be burned eventually. And let's say you have a combustion efficiency of 99% that is turned into CO2, or 98%. For CO2 emissions, this doesn't really matter that much. It's kind of a less than 1%. Or a percent error. But if you think if either 1% or 2% of the methane in the natural gas that you're trying to burn is kind of released before it's actually burned, that's 100% error. And that's why these uncertainties in methane emissions from the anthropogenic side are so uncertain, and simple bookkeeping is not really the way to go forward. Next slide, please. To make matters worse, the typical methane emissions are very heavy-tailed, follow a heavy-tail distribution. What that means is that a very few amount of sources are contributing most to the total flux. For those who know Pareto's law, who was actually an Italian economist, he came up with this 80-20 rule. And I think at that time, he basically found that about 80% of the land in Italy was owned by 20% of the population. This might ring a bell in many different areas as well, where 80% of the tax revenue is coming from 20% of the people and other parts in economics as well. And for methane, almost exactly the 80-20 rule holds as well. Animation, please. So we see here that about 80% of the total emissions in these oil and gas related activities are caused by the 20% of the biggest sources. And one example of one of these big sources, you can see here in the video on the left side, which is basically malfunctioning equipment. The vent is not really closing properly, and a lot of methane is being emitted at the same time. That is, in a way, also a good story, because if we are able to pinpoint to where these big emitters are, we would have a much better emission reduction strategy than having to follow millions and millions of these small sources. So there's a kind of a good message behind that as well. Next slide, please. So what's the impact of COVID? That's tricky. So we are thinking about this one And as Anne-Marie said before, it is hard to see any direct signals at the moment for methane. On the top, I show an example from the European Space Agency colleagues where they use the Tropomi instrument and then a commercial satellite that tries to do something similar to what we do from the aircraft on the right-hand side, where individual plumes can be mapped. But this story might be kind of related to kind of the particular weather conditions at the same time as well. So it's hard to draw any strong conclusions. But these are just some food for thought. In principle, we know that the industrial oil and gas demand is definitely down. The gas storage facilities are full. Household consumption definitely changed when people are staying at home. Me, for my part, in March, it was pretty cold, so we definitely had the gas on quite often at home. And what is most interesting is actually how these heavy tail, these big plumes and big emissions actually change under a COVID scenario, because they might actually depend on maintenance. So if you think about malfunctioning equipment and the oil and gas industry not sending out as many people as they have before, it might actually shift the balance there and increase emissions. So we are really not yet totally sure in which way it is going, but we have a California campaign planned. Hopefully this will kind of be happening in the near future to compare point source behavior with pre-COVID data. And with that, I'll conclude my talk and hand over to Paul, who can say a lot more of actual change related to actual changes in the atmosphere, because he can look at very short-lived gases.
Thank you, Christian. Could I get the first slide then? So many of you have probably seen images such as this. This is from the same, one of the same satellite sensors that Christian mentioned, called Tropomi. These are observations of a pollutant called nitrogen dioxide, NO2. What's shown on the right side is a long-term average for this period from late March through late April for the period 2017 to 2019. And then on the left side is the same period, but this year. And NO2, unlike methane and CO2, has a very short lifetime, something like a few hours under typical conditions. And as a result, then we can see in NO2, we can see directly the dramatic drops in emissions that happened in a number of cities. So here we can see, for example, in Delhi and Lahore and in Mumbai, just dramatic drops in the concentrations of this major pollutant. If we go to the next slide, a similar set of figures is illustrated for California. Once again, on the left side, we see the change from the period, the longer term average. We can see that in Los Angeles and San Francisco, significant drops in the mean concentrations of nitrogen dioxide. So the question is then, given these large changes in the emissions of this one particular pollutant, how does that then respond into air quality? And this is a great test of a lot of theory for air quality abatement, to learn how does air quality change in different cities and different places in response to these changes in the NOx emissions. And it's one that's really taking a lot of our community's attention right now, because it is such an important unnatural experiment that allows us to study air pollution chemistry. So if we go to the next slide. So this is the Los Angeles Times, and this is mid-April, and this is an opinion piece. The coronavirus shutdowns are making it undeniable clear how toxic our car culture is. And along with this were these beautiful images of a beautiful air quality in Los Angeles, so you can see up to St. Gabriel's from downtown and beyond. A week later, the next article, so if you show the next slide, says coronavirus clean air streak has come to an end. And why is that? By June 2nd, we had some of the highest ozone levels that had been observed in the last few years. So I guess this again illustrates, much like the discussion by Christian and Anne-Marie, that these are complicated things. And when we see changes in emissions, it doesn't necessarily translate directly into the improvements in air quality. It's going to depend a lot on the natural chemistry of the individual cities in which these emission changes happen. So if we go to the next slide, We can look at Los Angeles as seen through the Air Quality Management District. So on the left is the same pollutant, nitrogen dioxide, but now measured at the surface. What's shown in the black line is the historical data from 2015 through 2019, shown as a function of the time, the day of the year. So this year is shown in green before the shutdown, and then in red after. Again, so we can see this dramatic difference between this year and previous years, at least in April and May. But notice also that these blue periods, those are the periods when we have had a lot of rain in Los Angeles. And in fact, the weather plays a very important role in air pollution chemistry. This has been known for a long time. And we can see that this April in particular, as those of us who live in Los Angeles certainly know, was a particularly rainy period, one in which we would have anticipated air quality to be better just because of the atmospheric dynamics. The other context for this, for the data that we're looking at is shown on the right, which is a more long-term record of the amounts of NO2 here measured at the Pasadena Air Quality Monitoring Station just south of Caltech's campus. And so we can see over the years from 2000 to 2020 to this year, this dramatic decline in the amounts of nitrogen dioxide in the air. In fact, NO2 levels have been declining at about 6% per year over this entire record. This is driven by reductions in emissions, primarily from diesel engines. So diesel and high temperature combustion are the major sources of nitrogen dioxide pollution. And as a result of the changes in emission control technologies, we've seen this great reductions in the amount of NOx emitted over the years, such that 2020, while we've had this large change in the amount of traffic, in fact, is slightly anomalous. It definitely is lower. But part of that, as I mentioned, is just simply the weather. So the nitrogen dioxide levels that you see over a city like Los Angeles, again, they do reflect the emissions, but they reflect much more than that. If we go to the next slide. So this is a photograph of Ari Hagensmith, who did a number of important experiments at Caltech in the 50s, and then went on to lead California's Air Resources Board. He was the first president. And it was really his work that illustrated just how important the emissions from automobiles were towards the horrendous air quality of the basin at the time. As a result of his work, the emissions control systems that we all now have come to have on all of our cars, including those around most of the world, the emissions from automobiles have become really quite clean, especially in Los Angeles from gasoline cars. And so if we go on to the next slide then, we need to talk about and understand a little bit more how air pollution forms in a city like Los Angeles. And so what are these ingredients that make up the smog? So one of them is ozone. So ozone is actually produced in the atmosphere by photochemistry. So it requires the presence of sunlight and a number of other things, including nitrogen dioxide. So ozone is a respiratory antagonist, and it is also known to trigger asthma. It also damages crops. But when we see when we see smog, when we see something like this image on the right, what we're actually seeing is the scattering by small particles. These are called aerosols, and they're produced both from primary emissions, meaning directly from combustion. So think about the soot that comes out of a diesel truck as it's passing you going up a hill. But most of the particle mass that you see in this image on the right is actually produced by the oxidation of a number of chemicals in the air. And many of these chemicals are organics, such as unburnt gasoline and other things. So these organics that make up an important part of the air quality control strategies come from all sorts of sources. They come from those of us using smelly things to make our houses smell good, like cleaners and detergents and chemicals. They come from the biosphere. So trees are emitting a number of organic compounds. And they come from refineries. And yes, indeed, they also come from cars. But as the cars have become cleaner and cleaner, the emissions from all these other sources have become dominant. So notice that in this list of important air quality challenges, I did not include NOx or NO2. And so this thing that we see from space is really a catalyst for air pollution. And you only need a little bit of it to get the job done. And so even though we see these large reductions in NO2 in Los Angeles, it doesn't mean it's going to translate into improvements in air quality as seen from ozone and particles. So if we go to the next slide, what you can see here is the particulate matter in the basin. And again, the black is the historic data. The green is this year, and then in becoming red when we transition into the shutdown period. Notice again that this blue period, when it's raining, the amount of particles in the air is really low. That's when those pictures of Los Angeles happen, when people say, wow, it's so clear, it must be all the cars that are off the road that did this. When in fact, it was mostly just the rain. Once we get out of the rainy period, the particulate pollution is not so different from historical. We can see the same in ozone on the next slide. And it's the same thing. You can see, in fact, that there were these large differences, significant differences in April this year, but they're mostly associated with the weather. Following that, we had a number of very hot days. And once again, ozone pollution is right back at us. But this will be different in different cities. So if we go on back to the next slide, the last slide. So in Los Angeles, because we have worked so hard to clean up the emissions from cars, even though the car pollution has demonstrably gotten better over this last few months, the change in the things we care about, the particulate and the ozone, is not so much. This will be quite different in other cities. So in a number of cities in India, for example, where the organics were also greatly reduced. These come from the two-cycle engines that people pop around on. They come from all the industries that were shut down at this period. And indeed, they saw huge improvements in the amount of aerosol pollution and the increase in visibility. In fact, there were people living in India who, I think probably for the first time in their lives, experienced truly clear air. And so this experiment that happened is one which allows us to look at across this diverse set of cities each with their different organic loads. You have Linde with the trees, you have Seoul with the solvents, you have India with all of these other sources, and we can now look at what happened to air quality and understand how best to improve it, not just for us, but for inhabitants of the world. And so with that, I'll turn it back to Jessica to lead us in our questions and answers.
Thanks, Paul, and thank you for the great presentation, and also to Anne-Marie and Christian, who I'd like to welcome back on the screen. I saw several comments in the chat about how informative the presentations were, so thank you very much. So now we're going to move into our question and answer session, and I'm going to start with a couple of questions for each panelist, and then we'll move into the audience questions. Make sure that you are adding your questions to the Q&A area so that our panelists can have a chance to answer them in a little while. So let's start off with Anne-Marie. Anne-Marie, the other sort of big event that happened within recent memory in terms of the CO2 budget was the 2008 global recession. Can you kind of compare this COVID event to that recession in terms of how much the carbon budget was changed?
Mm-hmm. Yeah, no, that's a great analogy. So indeed, that global economic downturn did result in a reduction of carbon dioxide emissions. I actually looked up the numbers just before this. I don't carry around in my head, but there was about 1.5% reduction in 2009 compared to 2008. But the interesting thing then was in 2010, it came roaring back at much higher emissions, sort of making up for the loss. So that economic downturn definitely saw a decrease, not nearly as large as what we expect we'll see this year, but then it's the years following that'll be interesting to see how they pan out.
So I'm actually going to follow that up with a question that I've seen from the audience, and it's sort of a conglomeration of several people's questions. But you know, the forecast or the projection that you showed indicated, you know, CO2 going back to normal levels by the end of 2020. And so the question is, and we see that that happened actually even, you know, to increased values after the recession. So the question is, do you think that there are going to be longer term changes to the way people travel, the way people go to meetings or don't go to meetings and that sort of thing that would actually have a longer lasting impact on CO2? Or do you think it's likely to sort of recover and even go past where it was the way it did after the recession?
Yeah, no, I think that's a good question. And there's been a lot of discussion among many people. My perception right now is that, number one, you have to remember aviation is not that big of a piece of a pie. So let's say we all travel half as much as we used to. That's going to be kind of a small sliver in the budget. I do believe that the technology is different now than it was back in 2008 or 2001. Right after 9/11, aviation stopped. People didn't travel for a while, and we thought, oh, maybe we're going to change behavior. There was very little behavioral change, but now we have things like WebEx and Zoom and so and so. So perhaps we'll fly less. Will we drive less? Will we truck less? My guess is you'll see some modest decrease, but it's not going to be that amazing in the end. I certainly think humans are humans, and we're going to go back to our old habits unless we're really forced not to. That's my read.
Thanks. All right, so now we're going to move on to Christian. Christian, you talked a lot about how complicated the methane budget is and how we don't understand what happened to methane in the early 2000s when it flattened out, because it has all these sources and sinks and you have to think about all of them at the same time. So does that mean that direct measurement of anthropogenic sources, like you showed for the California map, is kind of the only way to understand what's happened with respect to methane during the COVID-19 period?
Not necessarily. I think in the next couple of months, we will probably also see more of the impact on the larger global scale. But for this, we really need more than just like a month or two of data to put this in perspective, as all the other speakers have alluded to, that weather and different changes in the transport patterns from year to year, and weather is kind of a dominant factor for interannual variations. And to really see whether in particular location, what we are seeing right now is just a consequence of interannual variation and transport or emissions that will require a little bit more analysis in the future. So it's hard to really do this with the limited amount of data that we have at a few locations at the moment. And it's very important to kind of keep running our kind of global background monitoring stations, because they are our only kind of reliable measurement stick to kind of what's the average methane concentration in the global atmosphere there. We can't really do this with the tools that we have from space or with the airborne imagery, which are great to detect kind of very localized sources, but to give you the exact number, what's the total amount of molecules in the global atmosphere in terms of methane or CO2, there we really need slightly different techniques. And I think I missed another part of the question. Is that right?
No, it was really focused on, do you have to actually measure the emissions directly, or will you be able to tease out from the global budget?
Yeah, it is just, the problem with methane is if we do typically inversions based on atmospheric data, it's hard to disentangle this directly between sources. If you think, for instance, about emissions from the Bakersfield area, where we might have near Tulare County a huge amount of livestock, basically cattle ranches, that might be co-emitting methane nearby the oil and gas industry. So if we see methane increasing and there's some indications that it's coming from these areas, disentangling where exactly it is coming from, which source is responsible for this, is relatively hard, and we would need to have additional tracers like methane isotopes in there to tease these out. If we have the airborne imagery where we can basically to the meter exactly say where the sources are coming from, there's no discussion about it. There we can directly pinpoint it. That's the strength of it. Quantitatively, it's not as robust as in situ measurements, but for finding the locations where things can be changed and improved, it's very powerful. And actually industry is also very much interested in this, because for them, it's very tedious to check like 80,000 well pets every other day to see whether there's a leak. If someone can tell them, look exactly at this, and this location, it's a win-win, I would say.
Right. Yeah, I know that the industry has actually been very thankful for the measurements that you guys have made, and it's helped them reduce costs, really. So, Paul, you talked about, you know, that we're collecting all this data and we're doing this analysis and that it can help us understand how to effectively control air pollution. Can you talk about that a little bit more? What specific things can we learn from this event that will help us sort of feed science into effective policymaking?
Yeah, so there's, again, I think one of the things we've learned in our learning is the diversity of response to the changes in the different cities. And it illustrates again how the control strategies must be different for different places. And so just as an example, I think we've come to realize that we've run out of improvements from the car modifications. So the monies that we spend on continuing to make cars cleaner and cleaner might not be our best investment in a place like Los Angeles. You know, that there are other lower lying fruit. You know, we shouldn't be using 2-cycle engines to do lawn mowing. We need to work on many other aspects of the organic chemistry that's being in a place like LA. In a place like India, I think really I'm going to be most interested to see about the interplay between public perception and policy. Does the fact that people have now had an example of air quality improvements similar to what we saw in LA, but that evolved over decades, you know, will that lead to demands on society to address the pollution problem, which is really quite horrendous in a lot of the world? You know, LA is still the most polluted city in North America, but it pales in comparison to what people are exposed to in many of the cities of Southeast Asia, for example.
Yeah, it kind of seems like once you're able to see the Himalayas from your house, you don't want to give that up again.
Yeah, one hopes, because, you know, I think one of the things we've shown in LA is that with sufficient application of technology, these problems are solvable. I think it's actually true of a lot of our problems, right? I think the solutions to the climate problem are now at hand, and it's in many ways it's how do those get applied, and how can we see them being applied at a faster pace? And maybe some of these changes we've seen as a result of COVID in the environment will help that conversation further.
Okay, that's actually a great segue into the next question that I had for Anne-Marie, which is, you know, it's clear from your presentation that realizing any sort of significant change in atmospheric CO2 concentrations is going to require very large scale sustained changes beyond just that we're seeing to personal transportation primarily. We are currently at about 417 parts per million of carbon dioxide in the atmosphere. Can you just give us an idea of what would actually be required to get back down to 400 parts per million, say, by, you know, over the next 50 years or so?
Yeah, so when you think about, as I mentioned, carbon dioxide is really long-lived in the atmosphere. So let's say we were able to modify our transport system and all of our electrical generation and industry. And let's just pretend we changed all those things, but we couldn't change the airplanes. We're still emitting some carbon dioxide. So you're not going to actually be on a decreasing path. In, you know, general, the Earth's atmosphere, ocean, and plants tend to just stay in balance. So if we just stopped emitting, we'd be almost kind of on a flat line. So to get down to 407, we need to actually take some positive action, like putting more trees all around the globe. So we have trees reducing carbon dioxide and drawing it back down into plants. Some people are testing out active carbon dioxide removal mechanisms from the atmosphere. We'd have to see if those technologies can pan out. And I'm sure Christian and Paul probably have some other ideas of new technologies available to try to draw carbon dioxide out of the atmosphere. But we need both emissions reductions and active removal of carbon dioxide if we really want to make a dramatic change over the next 5 decades.
Okay.
It's a challenge, a technology challenge for all of us, for sure.
Yeah, I mean, that actually leads again into another question from the audience. And this one is from, let's see, sorry, I've lost it now. Well, I'll just go ahead and ask the question. So the idea is, you know, it takes a lot of work to reduce emissions, to remove carbon dioxide from the atmosphere. And so, so the question was sort of, what is your take on geoengineering as a way to reduce the incoming solar radiation so that we can sort of cool the planet while we're working on those solutions? And I'm going to give this one to Paul.
Well, I'm actually working on a National Academy study right now directly on this question of what research should be done in the area of management of solar radiation, as it's called. And I have to say, there's two aspects to that. There's a suggestion that some of these technologies might be used, as the questioner mentioned, to essentially mitigate the worst heating that would come in the next decades. But it is absolutely no solution at all for the long-term problem that we have and we're making for ourselves with the CO2 emissions. If we continue to emit CO2, the oceans will continue to become more acidic, no matter what we do in terms of solar radiation. And so while there may be a role in a real emergency that these technologies might be considered for, they aren't the answer at all. The answer really must lie in us generating power for the planet without emitting greenhouse gases. That is the real solution here, and it's not one that's out of our reach.
Okay, good. That's optimistic sounding. So, all right, thank you. So I have one final question for Christian, and then we'll head over to the audience Q&A. So Christian, we talked in the beginning about how methane is both a sort of powerful climate gas and it's also a contributor to poor air quality. Can you explain sort of how and why it lies at this intersection between air quality and climate?
And that's a good question, Jessica. Yes, you are right. In principle, it lies right in between the topic that Paul talked about, but it's just more related to air quality, and what Avery talked about, which is just more related to CO2, where people often confuse greenhouse gases with air quality and think it would be bad for kind of people breathing air with a lot of CO2, which is kind of really not true, because otherwise you should not be indoors because there's a lot more CO2 typically if you close your windows. Methane is a little bit different because it is not like CO2 inert in the atmosphere, but basically reacts through photochemistry, and it can lead to increased ozone concentrations at the surface as well. So that's one primary focus. But you shouldn't think about it that if you have a little bit more methane in LA than elsewhere, the air quality in LA is worse because of methane. This is more changing kind of the global background tropospheric ozone concentrations, which might have impact on things like crop yield or just the likelihood of exceeding the ozone concentrations that are kind of harmful for mankind. But it's more a global effect than a local effect. The other part is also that once atmospheric methane goes into the stratosphere, it also oxidizes to water vapor. And that's another indirect effect where basically we are increasing stratospheric water vapor, which is again another greenhouse gas. So in terms of methane, I would say even if methane wouldn't be a greenhouse gas, we should be doing something about it. So it lies really at this nexus between kind of air quality, more on the background sense, not locally necessarily, and the greenhouse gas effects. At the same time, there might be co-emissions from other higher hydrocarbons that might have local effects from the industry in terms of methane emissions.
Okay, in the interest of time, I think we're going to head over to the audience questions. So it's clear that everyone has been heavily engaged in the discussion, and we thank you for all of the questions. Unfortunately, we probably won't be able to get to all of them, but we will try to fit in as many as we can. So let's see. So our first question is from Joel Haber, and I'm going to give this one to Paul. So Paul, in terms of Los Angeles, if emission reductions from personal vehicles don't help much anymore with respect to improving air quality, what are the emission sources that we should be targeting for reduction?
Yes, Joe, that's a great question, and one that we're actually hoping to learn more about. So we actually have a small experiment going on in campus right now to measure that mix of chemicals and try to identify what the sources are that drive the air pollution chemistry. But it's no doubt that there's a lot of chemicals that are used in our homes, in our businesses, even things like emissions from asphalt start to become important once the cars are as clean as they are. And so it's really through efforts to improve our understanding of what the air quality chemistry is in LA by actually making observations that we're going to learn what the best abatement strategies are.
Okay. And then Anne-Marie, in a similar sense, then what are sort of the biggest sources that we should be targeting for CO2 emission reductions?
Yeah, so I think we probably all actually have a good feel for what that is. If you spent a little time and created your own CO2 budget, you can often learn about the things you're doing and changes you might make. So I know for me personally, international air travel is a terrible contributor to my personal CO2 emission. So if I travel a lot less, that would really help cut things down. I also try to take my bike around town instead of driving my car, because driving is another contributor. And then, you know, and there's two other ones we don't often think about. And one of those is food choices. Production of meat turns out to be really pretty important. And if we all ate less meat, we'd all contribute less to CO2 emissions. And then my favorite one is buying stuff. Just production of stuff in industry is part of what drives industry. If you bought less, you'd contribute less. So driving, flying, buying, and meat. There's my list.
All right, thanks. And Christian, wouldn't reduced consumption of meat also lead to then less methane emissions?
Yes, absolutely. So a lot of the methane emissions that are basically coming from the agricultural side are related to meat production as well. It's mostly coming from ruminants, basically, that cows emit a lot of methane, as we all know, and agriculture but that is not only meat related. If you look at rice paddies, so everywhere where we create like artificial habitats that are anaerobic, which is mostly like waterlogged soils where rice paddies typically work in, there will be a lot of methane being emitted because methanogens that produce methane, these microbes, are living in anaerobic conditions. And when we have soils where there's a lot of carbon and no oxygen, methane is going to appear. The same happens in landfills as well.
Great, thanks. All right, so now we're going to move on to a question from, and I apologize if I mispronounce your name, from Carlos Coimbra. And this is for Paul. So Carlos says, I've not seen a big change in aerosols due to the lockdown. So does this imply that the essential economy is the greatest contributor to aerosols and that changes to the non-essential economy won't really affect aerosols?
Carlos, that's a great question. And I think the key is that the chemistry is very nonlinear. And so while the emissions from essential businesses, so where we see, for example, these significant decline in the amount of nitrogen oxide pollution, if we're continuing to use roughly the same amount of petrochemicals in our homes and businesses and so forth, and the trees are still emitting what they're emitting, we may not expect to see such a large change in air pollution. So again, it goes right back to that same question we had earlier, which is, how do we get better air quality? And the answer will be, we need to understand what the emissions are, where they're coming from. And in places like Los Angeles, they're probably coming from all of us, which makes it a much harder problem than the car problem. The car problem in some ways was, okay, let's fix the cars. And then we had great improvements in air quality, and that's what we did. But now when we get to this point where, your choice of shampoo, the choice of cleaners that you're using in your homes, the businesses and what they're using to manufacture and paint stuff, it becomes such a big distributed source that it's a more challenging. It goes back to Christian's 80-20 rule, except in this case, all those little things may end up being the things that matter. And if I could just make one more comment about, how does a person make a big impact on the environment? And both Anne-Marie and Christian talked and focused on this idea that there are personal choices we make to improve the environment. But I also want to say that in the context of Caltech and in the context of this community, we can make improvements by how we advocate for political change and how we invent stuff. How do we build new things? How do we monitor it? And how do we make that a translation to policy? And I think that's one of the great things in the Resnick Institute, where we're able to try to build upon that inventiveness and other things that I think is really the core of what we can contribute. It's great for us to all eat less meat and all those kinds of things. But I think our contribution can come through using our tools that we have at Caltech and places like Caltech to really make a difference.
Okay, thank you. So this next question is for Anne-Marie. It's from Aviad Levis. So you've mentioned that the dip in CO2 is small compared to the already existing atmospheric CO2, but of course that's a sort of a globally averaged picture. So the question is whether you are able to see a stronger signal close to emitting sources.
Yeah, no, that's a great question. And we certainly also did that math, right? I looked at global emissions and I said, well, it really happens more in land and over cities. So what's going to happen in a very local area? And I have to say, we've not yet found that telltale signal. And part of it's the reason that Paul mentioned, that if the weather's kind of different this year than another year, it's harder to pull it out. And then even in LA, things like we had a lot of rain, we have a lot of plant activity, those plants draw CO2 out, so they might change what this April or March looks like compared to another one. So it is true there's more CO2 in certain emission hotspots, but finding the change of emissions and its influence on the atmosphere is still difficult to do with the weather and the plant impacts that also can change concentrations.
Okay, and on a somewhat related note, we have a question from Jim Margatan about, in your presentation, you showed bunkers being a fairly large emission source for CO2. What exactly are bunkers and why do they release so much CO2?
Oh, Jim. So I believe, and anyone who knows Paul, Christian can pipe up here. I think the
bunker fuel, right? So shipping, yeah.
Ah, okay. All right.
Thank you.
All right. So I think we have time for just one more question. Let's see. So this is for Christian, and this is from David Law and James Stana. And the question is regarding the methane hiatus and increase that happened in the early 2000s and then later 2000s, the increase. So does this correspond to any given world event, the recession, 9/11, et cetera, or is there another theory that explains that flattening of the methane curve?
Oh, believe me, I lost all my hair about this question. It's still a tricky one to tackle. In terms of world events, there are people who speculate that the kind of leveling off that happened in the 90s a little bit was related to the collapse of the Soviet Union. In terms of the methane hiatus and increase, we are more and more confident that actually the stagnation period is a little bit more of an anomaly than the recent increase again. And there are theories that we developed that might be more related to an increase in the atmospheric sink of methane during that time period, maybe co-related to some stagnation or downward trend in kind of natural sources like from wetlands that were masking out the anthropogenic increases that we were expecting during that time period. And maybe these things just played out together during the hiatus and the increases just like back to business as usual. If you take the two time series and stitch them together, ignoring the kind of leveling off period in the middle, it actually looks very consistent. But that's the frustrating part about the methane is it's hard to draw any very conclusive conclusions at the moment. So there's still some uncertainties related to that, but it's a combination of factors.
All right, well, I'd like to give a big thank you to all of our panelists who I think have done a fantastic job this evening. And so thank you to all of you, and we look forward to hearing more about the outcomes of your work further down the road. Thanks, everyone. And then I'd also like to thank the team that's working behind the scenes to make all this run so smoothly, and especially Josh Loeffner and Matthias Kiel for helping to organize the questions from the audience. I really appreciate that help. And finally, I'd like to thank the audience for their participation in this discussion and for being so engaged despite the limitations of having to do things virtually. So that concludes our discussion for the evening, and I hope you all enjoyed it as much as I did, and good night.